Hello and welcome, and thank you for joining me in this seminar. Today I will talk about abstraction, xtUML modeling, and domain-specific languages. First, I want to thank the xtUML.org community and website for providing a nexus of information sharing that is helping to broaden the awareness of executable and translatable UML in the engineering community. It's providing a place for those with experience to link up and learn from one another, and as well as providing an exchange of documentation, videos, and source code to expand the capabilities of the tools used for executable and translatable UML. This is one seminar in a series covering anything and everything related to executable UML. These seminars are prepared by various community members having different experiences, and the hope is that by sharing these we can all grow and learn more. These seminars are recorded, so they will be accessible for you to download or to review on a YouTube channel, where you can go backwards or forwards and even skip the parts that you want to move on through more quickly. My plan for this presentation is to start directly with an introductory demonstration of a domain-specific language modeled in executable UML. After that demo, which will be very quick and maybe even confusing, we'll come back and have some discussion on abstraction, modeling, and some background on domain-specific languages, at which time we will come back to running in the Bridgepoint tool and show the way that domain-specific languages can be modeled using executable UML. For the topic of the first demo, I want to show a model of a domain-specific language for a microwave oven. Now, a microwave oven is a fairly simple device, yet it does need to be given instructions by its user. The microwave oven has some specific capabilities, namely a magnetron tube can be activated to heat up the food at various powers and in a mode that might be appropriate for defrosting. Inside the cabinet of the oven is a rotating plate that spins to make sure that the heat is applied evenly for the food that's in the cabinet. There is a timer that is used to control how long the food is cooked. Now, the way that the microwave oven is going to be used when a user wants to cook a particular meal cannot be predicted by the oven manufacturer. Therefore, he supplies a user interface that allows the user, in effect, to program the microwave oven using a domain-specific language. Now, the set of instructions that a microwave oven can execute are fairly simple, and there's only a few of them. For example, a defrost instruction that can slowly thaw some frozen food. A cook instruction, spinning to rotate this platter on the inside. Stop. Also some delay instructions and maybe some test instructions. So the user will enter on the front panel of the microwave oven some time instructions and choose a few buttons that in effect put together a domain-specific language program that will then be executed by the oven to sequence the defrost, the cooking, the delays, and spinning that are required to cook this particular meal. Here we have an xtUML model of a domain-specific language, including the domain-specific language virtual machine, together with a client application. Here we see the component that represents the domain-specific language. This is an execution unit that will interpret the instructions and execute them. This component represents the client application that will send the instructions to this component. Interfaces are defined that give the list of messages that can be sent into and out of these components, and we have various data types and constants defined. A configured system package shows the client application component actually connected to the domain-specific language component, such that messages can pass across the interface between these two components. To illustrate this further, we can look at a sequence diagram that outlines the time sequence of messages between the client application component and the domain-specific language. So this shows how it works. The client application will send a domain-specific language program in the form of a load message to the domain-specific language component, which will respond that the program is loaded once the commands have been interpreted and loaded into the memory of the language machine. Then at a later time, the application can send a run command and give the name of the program that was previously loaded, at which time the DSL component will execute that domain-specific language program, and when it completes, will respond back to the client component with a message that says finished. Now let's see what the internal behavior of this component looks like. Inside this component are some packages that define the domain-specific language itself. This class diagram shows a program class and an instruction class with subtype instruction classes that can run. Next, we will look at application-specific instructions. This is a domain-specific language program, and so we will move inside the component to find a set of commands for a microwave oven. We have a class diagram that shows we have 5 specific instructions in this language that work for a microwave oven. Defrost instruction, a cook, spinning of the food spinner on the inside of the oven, and we can reverse and stop. In the client application, a sequence of these instructions have been prepared in the form of a domain-specific language program to perform the cooking of some particular meal in this oven. And the sequence is given here, where we will start by sending a spin instruction to cause the food spinner on the inside to begin spinning. We will enable defrost mode and delay for 5 seconds in the defrost mode. We will then move to cook mode and begin a loop that will spin 3 times using a delay, and at the end of each delay cause the spinning to reverse. So this represents a small domain-specific language program sent from the client application component into the domain-specific language component. To actually run this in Bridgepoint, we can switch perspective to a debugging perspective, where we will launch the model verifier to run the domain-specific language program. So we see in the console here that we've executed the defrost and cooking. We've begun spinning, and now we are reversing the spin and delaying according to that program, and we should complete with a stop command. Stop cooking. Let us discuss abstraction for a moment. Modeling is a way of capturing our reasoning for a particular subject matter, our design, and highlighting the good parts and leaving out the parts that don't matter. So modeling is actually a form of abstraction where we identify the important stuff and exclude irrelevant details. More detail in a model is not necessarily better. In fact, a good model captures the simplest representation of a solution while leaving out the additional complexity of details that are not needed. Imagine that you could measure the distance between some idea that you have and an implementation of that idea into an engineering product of some sort. In engineering, that's what we do. We take ideas or concepts in people's minds and we turn them into implementations, into products, into services that people can use. And we travel a particular engineering path to do that. So imagine you could measure the distance of that path in terms of the time and effort that it takes to go from idea to concept, or go from idea to implementation. Modeling gives us an alternative path from the idea to the implementation, and it's a two-step path. First step, converting the idea into a model. Second step, converting the model into the implementation. Now, the steps are not identical, and the building of a model is something that we must do with our hands and our minds, and the conversion of that model to an implementation, however, can be automated, perhaps with a model compiler. So the distance, if we're using manual techniques only, the distance from the idea to the implementation is longer than the distance from the idea to the model, and therefore it is less work, less time and effort to do modeling, under the assumption that we have some automation to convert the model to the implementation in the final step. Through the years, various forms of modeling have raised the level of abstraction in which we model our designs and programs. In early years, we programmed in machine code and assembly, and over time, new languages emerged that raised the level of abstraction, including in recent years executable UML, which represents another step up the staircase of levels of abstraction, getting us closer and closer to working at the idea or concept level. Domain-specific languages represent another step even above the executable UML to allow us to be more productive, working at a higher level of abstraction, and shortening the distance between the idea and the model. So going back to our distance diagram from before, we now can consider that this distance between the idea and the model may be shortened just a little bit more using domain-specific languages, reducing the amount of time and effort that are required for our designs. And so modeling and modeling with domain-specific languages provide another means of increasing our productivity and allowing us to work faster and easier. Let's define domain-specific language. Martin Fowler has written a book, and in his book he defines domain-specific language as a computer programming language of limited expressiveness focused on a particular domain. So it's a language that has a very narrow and special purpose and is easy to use for that special purpose, and in fact might be the ideal way to address that specific purpose. Domain-specific languages are especially useful in devices where a combination of the use of the sensors and actuators cannot be predicted for the future. The example of the microwave oven, the manufacturer knows that the magnetron tube needs to be turned on, that the platter needs to be spun, but the manufacturer does not know how long and in which sequence and whether defrost needs to be supplied. And so the portions that can be predicted, the fact that the cabinet needs to be heated and the food needs to be spun on the inside, can be implemented in the hardware and software of the system. Still, a means needs to be supplied to the user to sequence that activity, and thus the idea of a domain-specific language for a microwave oven is useful. Another example is an autosampler. The sequencing of the sensor actuator control through a DSL allows the hardware and the embedded control of a device to be fixed at design time, while allowing flexible use when the device is in the hands of the user. Another device that can use a domain-specific language is an autosampler, and I will introduce how an autosampler works here, because in another demo to follow we will show a domain-specific language for the autosampler. The autosampler is a device used in chemistry and biology labs and has two main parts. It has this round part that contains the samples referred to as the carousel, and this carousel spins around, and inside the carousel are little bottles or test tubes. Back here in the back we see a sampling probe or a sampling needle that moves up and down and moves into the sample vials to either put fluid into the test tube or to pull fluid out. Here's another model of a autosampler that you can see the carousel with very tiny holes used for small test tubes, and the sampling needle here, which moves up and down and goes into the test tubes. The autosampler can be viewed as a set of sensors and actuators with some primitive commands. The autosampler needs the command to send the carousel to the home position where it would start. It needs an instruction that allows the carousel to move from one position to the next, and a couple more instructions that it needs to move the sampling needle up, and it needs to move the sampling needle down. And hopefully the device is smart enough to move the sampling needle up before it tries to move the carousel to the next position. A user could put together an autosampler domain-specific language program that might look like this. Here's a program to take 5 samples of 1 minute each, and perhaps the carousel has room for more than 5 samples, but again, the manufacturer cannot predict exactly how the user intends to use the sampler, and in this case it's not going to be a full carousel, it's only going to have 5 samples, and each sample is going to be operated on for 1 minute. So the first instruction would be to send the carousel to the home position, and then have a loop instruction that groups these next 4 instructions together and repeats them 5 times, sending the sampling needle up, moving the carousel to the next position, moving the sampling needle down, staying in that test tube for 60 seconds, repeat 5 times, and then at the end move the sampling needle back up and send the carousel back to the home position. Now, with the autosampler application in the backs of our minds as the target for our domain-specific language, let's consider how we would use executable UML to model a domain-specific language. First, we would abstract, identifying the important stuff and leaving out the irrelevant details, and identify that the parts of a programming language are program, instruction, opcode, parameter, and then build an xtUML model of just exactly that. And here we have a model that shows a class diagram of the program class that has a relationship to its first instruction, and the instruction has subtype instructions that include delay, while loop, for loop, and if. xtUML can be used to define the instruction set and its behavior. There are many DSL tools that are available and use these to parse and validate your instruction set. But what we'll show here is using xtUML to define that instruction set and define the behavior in an embedded electronics application. Most DSLs share a common need for certain general programming constructs, such as testing the conditionality with an if statement, or looping up instructions either by iterating through a set or by looping on a condition. And delay is especially in industrial devices like ovens and autosamplers, being able to program a delay is fundamental to almost all DSLs, and therefore these can be made common and reused between the various DSLs that you build. In the xtUML model of the domain-specific language, we have an application component that may be a user interface, perhaps on the oven or on the autosampler, which will send the program through an interface to the domain-specific language interpreting component. Here's a sequence diagram that shows the order in which that would occur. So the client application will first send a load command to load the program. So if you push the buttons on your microwave oven, first you're loading the program before you hit the start command. And as that program is loaded, the acknowledgement that it's loaded will come back from the DSL component. On the oven, you want to hit start. On the autosampler, likewise, when you're ready to start your experiment, the application will say it's time to run my domain-specific language program. Will provide as a parameter the identifier, so the name of the program that I want to run in case there's more than one program. And then the DSL will interpret that program, run it, and respond with a message that says that the program is finished. This program model is found inside the DSL component, and it is the model of the language itself, having the common shared language parts and then the specific language instructions being in these off-page connectors. One of those was the DSL for cooking, which we looked at the beginning of the presentation, and has the instructions defrost, cook, spin, reverse, and stop. The autosampler has an even simpler domain-specific language set, which include sending the carousel to the home position, carousel next, needle up, needle down. These four instructions combined with the delay and looping instructions provide a great deal of flexibility in the way that the autosampler can be programmed at runtime. Coming back to Bridgepoint, we see our system package again with the client application. Now the client application being the user interface of the autosampler, sending instructions across the user interface to the component. The internal behavior of the component is defined as a set of packages with the virtual machine class diagram, having the program, the instances of instruction related to each other, with the core set of control instructions, and then a link to the Autosampler class diagram package, having the specific domain-specific instructions for Autosampler, with the motion of the carousel and the motion of the needle being controlled. We can now run a domain-specific language program that will run the Autosampler through 5 samples using our needle up, our home, and our looping constructs. So I will fire up the xtUML engine here, run this program, and see that we are sampling, delaying, sampling now on the next sample, and iterating through a domain-specific language program that was defined through the user interface at runtime. And we've defined the behavior for each of those instructions using executable UML in a way that will allow us to build the device and yet have the flexibility to run domain-specific language programs driven through a user interface. Switching from the model debugging perspective to the C++ perspective, we can now build this model. By build, I mean invoke the model compiler and the C compiler. The model compiler will generate embedded C code from the xtUML model, and then using GCC will compile it into a binary which we can then run. The expected behavior when we see it run will be the same behavior that we saw when we ran the model verifier. Executable UML follows a set of execution rules that allows you to test your model interpretively from inside the xtUML modeling tool inside Bridgepoint, and then the model compiler has the role of translating that application into an equivalent application on a different target, and in this case C for embedded, or C code to just run on the workstation here. We can see the same behavior when we run it. We can explore the generated code and see that we've got lots of files. So let's look at the carousel home class, and in the generated code we've got nicely commented and highlighted code, and here's the class was converted into a C struct, and the state machine in this class was turned into executable C code. Here's the load operation on the command. Notice that we have generated comments for the action language right into the code. We can do more exploring, changing our model, regenerating it, adding features until we're satisfied. This concludes the presentation on abstraction, xtUML modeling, and domain-specific languages. I hope you find it useful, and please look for additional seminars at xtUML.org and in this xtUML learning series. Thank you very much.